Welcome to One-Click LCA Summer School session number 5, Materials and Methods. My name is Panu Pasanen. I'm the CEO of One-Click LCA and I'm hosting this session. Hope you will find this useful and interesting. We keep the same rules in the summer school as in the previous sessions, so microphones muted. Don't ask questions in the chat, use the Zoom's Q&A function. They will be answered live only in the Q&A part of the session in the end. However, I have some colleagues on the call who may be able to answer your questions during the session already. Today being Friday, so recording and slides are not going to be available tomorrow, but rather on Monday of next week. So without further ado, let us proceed. Today, we are going to be talking about construction materials and construction methods. And the purpose of this meeting is that you will understand what are the main materials, what are some of the pros and cons of those, what are the environmental impact considerations you should be considering when you try to specify or choose them for your projects. And also we are touching very lightly only though how this works with One-Click LCA database. If you think about it in a bit different way, the purpose here is to give you background understanding of why construction materials have certain environmental impact. So not just so that you have heard that something has a high impact or low impact, but you understand why that is and what's driving that. So you are not put to shame on the first time somebody asks you the question, why does steel have a high carbon footprint? If you didn't already join our LinkedIn group, you are welcome to do so. You'll find it on LinkedIn by searching for LCA Made Easy. Today's agenda is split into 6 parts. I will start by talking about main construction and deconstruction methods. After this, I will give an overview of construction materials, all of them. And after that, I will dive separately into cement and concrete, and then steel and aluminium, right? And these are the 2 main, let's say, construction materials by climate impact. And then in the other section, we will discuss all the other main construction materials. There are many construction materials we can't cover separately, but today we just have 2 hours. We also need to get you to your weekend activities. So we'll just go through these things, and you're obviously welcome to read more about materials we don't cover here, or more specialized materials, let's say. Finally, short homework and Q&A. And as I said, you can also ask questions in the Q&A functionality, and my colleagues might be taking them during the session. So now we are going to the main construction and deconstruction methods. Predominantly, we can say that there are 3 construction methods, let's say, or typologies, right? So we have on-site construction, where the structure and enclosure are built on site. This is typically having somewhat longer construction time, because if it's ready-mix concrete, you have to install the formwork first, then pour the concrete, wait for it to cure, and then go to next level and so on. It typically leads to longer construction time, and it may create more mixed waste, because separating the waste streams can be a bit more tedious when you are building on a site. In particular, for concrete buildings, this uses more material. However, for timber buildings, because much of the on-site construction is thick frame, as you can see here, and not massive timber, it actually uses less material. So no one size fits all rule here. Then we have prefabrication and assembly. In prefabrication assembly, elements are made in factory and they are assembled on site. So the connections between the elements, they are typically installed in factory, or they are ready to install using other methods. This is faster, and this creates less site wastage. Obviously, there's going to be wastage on the construction material making factory, but hopefully it's better managed because it's industrial conditions and there are less types of materials to separate there. In particular for concrete buildings, this is typically clearly more material efficient choice. And we have modular buildings, which are large building blocks, container-like usually, which are made in factory and lifted on place. This is typically very quick. Material efficiency varies, so they may not always be more material efficient because they are typically made for accommodating multiple floors being stacked, maybe up to 3 or 4 floors. And this actually may use more material than building a specific building for 1 or 2 floors because you can do it slightly lighter. They also may be more massive than a comparable building which would not be designed to be movable. But on the other hand, if movability is a benefit, it's obviously extremely desirable. The last today still a niche application is 3D printing buildings, which already is done to some extent, for example, by Mighty Buildings in California. We can expect that to also grow. I wouldn't classify it under any of these categories though. So we have on-site prefabrication and modular. And all of these construction methods can be used with most of the main materials. In the on-site construction, wood is typically stick frame, or is also called platform. It's very material efficient because it doesn't require as much wood as massive timber, but it may need weather protection. Concrete cast in place, as I said previously, it uses a lot of concrete in cold climates. In the winter conditions especially, concrete may need heat to prevent it from cracking during curing time. Cast in place concrete is not literally impossible, but practically impossible to reuse. So it's one-way building, and in that sense, of course, it would be desirable to consider other options if such are available. There's not too much by way of on-site construction for steel, because steel frames tend to be made in prefabricated for purpose. However, there are stone, brick, and rammed earth and other smaller material categories which can be readily used constructed on the site, typically for low-rise buildings. In less advanced economies, they are also used sometimes for a bit taller buildings, but they are of course very seismically dangerous, so they might collapse if you don't use, let's say, strong structural materials. So those are the main on-site construction material application methods. Then in the prefabrication and assembly, so there are different types of wood elements. You have cross-laminated timber / glulam. We have LVL, other glue reinforcement based timber, and we also have wooden, let's say, stick frame-like elements, which combine the lightness of stick frame with the prefabrication. Some of these prefabricated wood elements, the massive ones, use more material, but they are faster to build, and the speed of construction does provide the benefit, of course, of less likely needing weather protection, and also shorter site duration, which saves energy as well. Prefabricated concrete elements are more material efficient, and the initial curing of the concrete takes place in factory. Steel frame buildings are usually factory-made structures, completely made to customer spec to optimize amount of steel, so highly material efficient, and enclosure is assembled on top. And then we have a variation of any of these previous themes, which would be using lightweight external walls with any type of structure, which makes it a bit lighter, especially beneficial, of course, in a seismic region to avoid mass of building shaking when an earthquake happens. And finally, in the category of modular buildings, modular wood buildings do exist, low carbon footprint, all very good. They may be easier damaged if moved. Just a note on that side. I did put the 3D printed buildings in this basket just to put them somewhere. And we do have modular steel buildings, which are basically just containers for people to live in, actually furnished and all that. So a bit nicer than the ship containers type. And the enclosure may have some assembly or cladding, depending on how the building is intended to be, let's say, presented to the users. Whatever approach you use for materials, this would be a 5R approach. And 5R approach intention is to go about choosing the materials and construction methods in the right way. And I would suggest always thinking about first, if there's something that you could refurbish. Second, after you end up with some choices for materials, reduce the materials use as far as you can. However, don't detriment the service life, performance, and also adaptability when a building could be adaptable for additional use cases. You may also replace some of the materials with other more environmentally considerate or lower cost materials, or otherwise having some benefits. And obviously in procurement phase, use as much reused material as you can and ensure future reuse by installing the materials so that the connections can be undone. And then all other things being equal, then buy low carbon products within the material category that you have ended up in. So that would be the 5R: refurbish, reduce, replace, reuse, and require low carbon. And this principle should be followed irrespectively of what material choices you make. First, this is a building where everything has been stripped down on the interiors. And you obviously can see that there's a great deal of materials in place. So if you can still make use of this frame, it's a very efficient approach to saving material. There's a comment about recycling isn't in this 5R. So indeed, that's a good point. I recommend rather suggesting reuse. So you don't actually remanufacture, but you would actually make sure things can be reused as products and not remanufactured. That would be the higher priority among those. Okay, so renovating and refurbishing uses far less material. Obviously, you can't make projects just by using one trick. So here I have an example of a project where I have highlighted about 10 main material categories by their preponderance of their, or by the share of embodied carbon they would have. And you have concrete, slab, structural steel, and gypsum board. And here you can have a design decarbonization strategy. So you can design them somewhat differently to reduce material use. However, once you have dealt with that matter, and not every material can be compressed infinitely, you are actually only able to buy the best possible material for those purposes. And here we have 5 material categories, from ready-mix concrete to insulation to rebar to mortar and glass, where our only choice is really to buy as low carbon as we can, or specify if we are not directly the buying organization. And we do have also some complete substitutions possible. So we could replace metal-based ducts in some building types, for example, with textile-based or plastic-based even, depending on the fire code, which are far less, having far less environmental impacts. Carpet flooring, likewise, we could substitute that completely with something different. Polished concrete flooring, for example, for some building types. So we can combine a number of strategies for any given project to achieve the best possible overall outcome. So I encourage you to think about the different strategies that you could use with different materials. Finally, when we talk about the demand reduction, there's 2 ways to think about it. Doing the same thing with as little as possible. So that's efficiency. And the second thing is sufficiency. So sufficing with as little as possible. Obviously, if your organization is just building to spec, you can't change the specs anymore. But if you are the designer, you can actually try to find clever ways to make better use of available space, maybe build one more apartment in the floor, or seeing if you can use some alternate standards. So is everything actually really possible that is usually done? You can't, work around regulations, but there's many other things you can try to design around. So consider this when you try to do low carbon buildings. Reducing mass is pretty much always reducing carbon, not literally always, but consider the material use of your choice, whichever choice you have. And then obviously the building will be dimensioned and the structures will be dimensioned or should be optimized for the actual load of the building and the intended functions. Example I particularly happen to like is removing retaining walls. I call this the IKEA style construction. So for some reason, many of the IKEAs I have been in, they have a, car deck under the building, but the building is standing on columns and there's no walls around it. And obviously there's they don't have any benefit from being there. They do cost money though, and they do cost carbon. So IKEA figured something out about environmental design, even though they didn't think about it in that sense, probably. Or I can tell you for sure that they didn't think about environmental design for these IKEAs in question. But all the same, the end goal is achieved in a similar manner. So there's a number of ways to build it, right? You can use different construction methods, you can use different construction materials, but usually it always ends up the same way. And that's called, wrecking ball. And they come with an excavator, they tear down the walls, apply a bit of old good wrecking ball, and maybe saw and cut a bit some of the elements. And mixed waste we get, which is not, let's say, ideal in terms of preserving the value of materials. So when you choose your construction method, please do consider deconstructibility and design it for disassembly. So make sure you will have undoable connections. They need to be, specified, they need to be designed, and they need to be implemented. And you can't just pour, screed on top of this one, like you need to put a cork or something else so you can access the connection later. And if you have connections that you need to embed, don't embed them in cement-based concrete. You can embed them in gypsum-based concrete, for example, so it's easier to open. And avoid chemical-based bonding, and do avoid nails if you can. So materials just can be simpler and unfastened. And you can have reuse elsewhere. So if a building has outlived its purpose, stuff can be taken out, it can be reused elsewhere, or the building itself can be reused, or the materials in the building can be adapted. For example, internal walls, very desirable to be able to move internal walls in an office building, for example, because when tenancy changes, often new tenants require some layout changes, and being able to do that with the same materials is of course great. So those are some of the options that you can enable by material choices which are conscious. So so much about the main construction and deconstruction methods. I will proceed now to give an overview of construction materials. And maybe this was already obvious for you, but if not, construction is really a huge material demand source. In the European Union, it's causing 1/2 of the material extraction. And obviously much of this is in infrastructure, so it's under the roads and railways and such things, but also in the buildings. And then when we consider the carbon emissions, where does it come from, right? And at the global level, as a proportion from IEA's global energy carbon emissions, we have cement being approximately 4 gigatons if you include the process emissions, and about 8% of global energy carbon emissions. Steel, 3 gigatons, about 6% of all. Aluminium, 1 gigaton or about 2% of all, and plastic about 1 gigaton, 2% of all, including incineration at the end of life, which is what you do for plastic. These figures do include process emissions as well, just to be sure. So they are slightly higher than the emissions, which would be only incorporating energy use emissions for the same materials. And then on top of this, you do obviously have other materials requiring energy and having process emissions, transport and site operations, refrigerant leakage, and the end-of-life processing of construction materials. So there's quite a lot, but the biggest sources indeed, they are clearly cement and steel. Aluminium and plastic as well should be certainly considered, but also those materials that you build with in your particular case. So if you have a brick facade building, the bricks obviously do greatly matter for your case. And we did some research about this and published it too. If you care to look at it, you can find it on our website later. But we did some building typology based impact distributions by materials, and this showing the difference between commercial, industrial, educational, office and residential buildings, and what portion of the impact is coming from concrete being the bottommost. So we are steadily in the range of 40 to 45 points of total impacts. Steel, which is varying more from about 20 to up to 40% for industrial buildings, which usually have a steel frame and steel enclosure also very often. Other metals, which is predominantly aluminium, but also copper, which is far more used in office buildings, which tend to have curtain walls consisting of glass and aluminium. Then insulation. The insulation shares here reflect, to be clear, building volume from EU. So this is a data set which is EU specific here. So if you are in a different climate, you may not have similar share of insulation. Then we have doors, windows, and glass. And as you would expect, windows are used in all building types, slightly more in office buildings, which tend to have these curtain walls. And other materials, well, depends, right? And you can find the data here under the link in the bottom later if you want to zoom into this. But this is just to give you an understanding of what it looks like at the building level in general. For your specific building, of course, the figures will vary based on the choices you make. For example, if you make a wood building, the wood is definitely going to be an impact driver. Then if we go into the construction material typologies, I'm grouping here the materials in 4 different categories: non-metal minerals, metal-based, chemical-based, and bio-based. And the bio-based here excludes bio-based chemicals, right, which are in the chemical-based basket. And then there's a 5th category, which in a way is largest, not by climate impact, but by number of SKUs. So the composites and assemblies combining multiple materials. And we're just going to dive into these a bit, looking at them from a few different angles to get you an overview of what kind of things we are dealing with here and why do you need to care about it and what to pay attention to. So here we have the, let's say, approximation of the main construction product value chains. And if we look at the top row, we are starting with the raw material extraction, moving to the raw material manufacturing, and then moving to a next step in the value chain, which is semi-finished product and final product. After a final product has been manufactured, it can be assembled into subsystems or systems. And we are going to be talking through the main material typologies and how are they made. This is an overview chart, and then we will dive into selected ones a bit later. And you can see a number of orange dots here on the chart. And the orange dots tell you basically which of these products are actually sold to projects directly, because there are many primary products and raw materials which are also sold to projects. So for example, construction projects buy also aggregates, they do buy cement, they buy sawn wood. They don't only buy the last final products category, because they can mix their own concrete, or they can use cement for screed or such things. And in the non-metallic minerals, there's stone, limestone, gypsum, and clay. And stone or natural aggregates, if available, is used, for example, for ready-mix concrete and asphalt. And it can be crushed, or it can be, just extracted from nature and maybe washed. Gypsum is used as an additive to a number of processes, including also, cement/concrete, and it's also used for gypsum products, obviously. And clay is then used for bricks and ceramics. And asphalt is a finished product in its own. There's no, let's say, refining happening after asphalt. However, cement is predominantly used in concrete, and concrete is then used in 2 forms or 3 forms, let's say. It's used as ready-mix concrete, which is basically poured in a fluid form into a mold, and in a precast form where the rebar is already placed in the form in the mold, and the product is left to cure in a factory. It's also used for concrete products which may not have a reinforcement, which is basically a category of precast products. Gypsum is used for making boards, for making screeds and other things, and is also used for making wall systems. So prefabricated wall systems is also a category which may sometimes be used. Then if we go to the metals, this we will cover a bit more in the case of steel and aluminum later, but it starts from the ore, goes through primary raw material manufacturing, and then it goes through various value-add layers. There are actually probably more value-add layers than shown here, but for simplicity, we are just showing a few. And steel, for one, is very often traded commodity. So steel traders buy steel from different places and provide it to fabricators and sometimes manufacturers. And they then make metal systems, they make metal frames and other things. Steel is also sold directly for making roofing, cladding, and other elements, as well as a number of different products. Aluminium, on the other hand, it goes through various refining steps from the smelter to be extruded, to made into profiles, for example, and incorporated, let's say, in windows or aluminum-based products such as facades and others. Wood, comes from the forest, goes to a sawmill, and then it's going to be used in different ways depending on the fraction. So if it's if it's sawn boards, it goes to boards. If it's chips, it goes to particle board and such like. And it can also go to more advanced manufacturing like glue lamination, cross lamination, and such like, which can be then used for making elements or even systems. And in the chemicals industry case, it starts with oil, natural gas, or other more, let's say, advanced basic chemicals or biochemicals, which are then made into plastic or other precursor chemicals, which are then further refined to make plastic products or building chemicals, and eventually plastic systems or other systems. So those are the main construction product value chains, and we'll cover some of them a bit later in the presentation. Short and partial overview of mineral-based construction materials from the least processed to the heavily thermally processed. There are obviously other types of processing than thermal processing, and this is not literally one directional, but to simplify, I just put it like this. So in the low processing end, we have rammed earth, crushed concrete, sun-dried bricks, natural stone, which doesn't obviously get any thermal processing, is more sawing and polishing and such like. There are some alternative mineral-based binders, such as blast furnace slag, ashes, which can be used in concrete, for example. There are gypsum products, which do go through thermal treatment. There's asphalt, which is heated for use. Fired bricks, which are fired in high temperature. Concrete, which is predominantly, just mix involving cement, but have to place it somewhere here. And then mineral wools, which are made by either heating glass or either heating stone. Glass itself, which is used, which is made from mineral-based materials, and cement made in very high temperatures, coming a bit later, and slaked lime, which is processed limestone, which is then treated with water. So there's a very big continuum of mineral-based construction materials, and typically the rule of thumb is the heavier the thermal processing, the heavier the process impacts, as well as the energy use impacts in manufacturing. So if you can think of this like, if something requires high temperatures, it's not like great from the point of view of environment, unless obviously we just have to have those performance criteria or characteristics that the thermal treatment affords us. So that's the overview of the mineral-based construction materials. For metals, it's a bit different. So all metals are made in high temperature. And when metals are compared with no recycled content in them, or there may be some in this profile, it's not like literally religious, but you can just say like it's highest being aluminium, copper being second, then stainless steel, structural steel, and rebar. So this is the rough order, or actually the actual order as well, of the virgin steel, virgin copper, virgin aluminium, and so on. So it goes from aluminium, copper, stainless steel, structural steel to reinforcement steel. This is the order. And obviously there's no commercially available substitutions that you could consider, because you only use them for a certain purpose because of cost and performance reasons. So you will never come to a trade-off where you would consider, or probably never come to a substitution where you would actually have a consideration of being able to change copper for steel, except in rare cases. Though it may be possible and desirable sometimes to use stainless as opposed to other type of steel for achieving longer service life or other parameters. All right, so that's about the metals, or metals used in construction, which is our interest today. And then I'm going to go through an overview in a fairly short form of the main environmental impact category, environmental impact parameters over a product's life cycle for each of these 5 categories of products, being mineral, metal, chemical, bio-based, and composites and assemblies, right? And mineral-based raw materials are easily extracted and typically local material. So it's not hard to get them, put a shovel in the ground, maybe take the topsoil off, and there you go, you have your stuff. Maybe not 100% purity, but the idea is that it's not hard to get to. Manufacturing is often requiring thermal treatment, and it may have chemical process causing further carbon impacts, especially for limestone and gypsum-based products. These products are often local but very massive materials. So you should always be mindful when you choose mineral-based materials that you are actually considering their transport impacts. There's a lot of natural stone being polished and cut in China, for example. So we ship, stone in big blocks to China, and then we buy it back as natural stone products in Finland, right? I'm completely stupid, but that's what's happening in the industry. So if you can influence that, please stop it, and don't let it happen on your projects if you can. They are very long-lasting products. They may carbonate in use if they have calcinated before they may carbonate. And because they are massive, they often have some form of thermal mass, and the thermal mass can have be favorable to reduce a bit or even out temperature extremes during the day. End of life, not so obvious usually, because these are hard but brittle materials, so they can't be bent or anything. So they kind of break in a bad way. So if you can't deconstruct them, you need to crush them. And it's a downgrading, so it's not a reuse or even recycling. But if it's deconstructible, you could certainly use a hollow core slab or a concrete column in another project. And sometimes that's done already. So much for mineral-based materials overview. Metal-based, so energy intensive to extract, often imported, or is also often coming from a distant location. And primary manufacturing is very energy intensive, and it also has process emissions besides the energy use emissions. These are global commodities. Steel is expensive per ton, so you can afford to transport it very long distances. They last very long, and they are easy to disassemble. You can recycle them forever, and they are so valuable as to be commercially salvaged. So no need for incentives to salvage them for recycling. But you need to have incentives for, reuse as materials. Chemical-based materials, they do have raw material upstream emissions on the oil field or in the natural gas leakages to the atmosphere in the transport. And the manufacturing impacts are mostly in precursor chemicals and far less in the, let's say, the injection of plastic into molds. So the final manufacturing tends not to be the most energy intensive for chemical-based products, at least for plastics, right? Transport depends a bit on the material, but it tends to be limited because they are not very expensive, per ton compared. So you can't afford to transport them very far usually, but you can transport them thousands of kilometers all the same. So, but not from across the globe as final products. Lifetime depends very much on application and exposure. Chemical-based products don't have it very easy in terms of end of life. So if things go well, they are incinerated. Otherwise, they tend to be landfilled. But there's more and more raw material recycling as long as everybody knows what exactly do you have in your product. So there's some light in the end of the tunnel for chemical-based products as well, at least for the ones which are not having a chemical bond with other materials. And then when we go to the bio-based, and so we can have wood or plant fiber, even wool or fungi, a bit more exotic, those last two. And these two store some bio-based carbon, which Stephen has discussed in a previous session. They are often relatively low impact, even if treated or even if glued and other things. Transport distances for these can be very long. They are quite light materials on one hand, and moreover, you can't get timber in commercial quantities in all the regions in the world. So locations like ours, we can export it a bit further, and hopefully you will buy a lot of finished timber, by the way. Timber is often treated in use, but it is a choice in some cases to do so, and it increases the maintenance, right? So if you do a timber facade and if you choose to paint it, or if you have to paint it, you actually basically make a choice also for having those life cycle emissions associated with applying paint so and so many times. In the end of life, timber and similar wood-based materials are, in the better cases, incinerated, unfortunately also landfilled in some locations, but they could be salvaged for new applications. And finally, composites and assemblies, best of both or any of these previous worlds, or maybe the worst when it comes to end of life. So they provide good combination of characteristics. So it's more desirable to have a window which is not made of the frame material because you wouldn't see through it, you know. And if you made it on all glass, then you would have, you know, wind blowing across the corners. These things, they can really be depending on what the actual product is. So they can be transported usually for some distance, but not infinitely so. So their value also per ton tends to be limited. And end of life may be a bit harder to recover for composites, but assemblies are quite good. So window you can uninstall and reuse in a different building. Same for door, and other products as well can be used as they are. So much for the short overview. Then if you happen to work in the European Union or European Economic Area, we have two particular regulations, well, many more, but two particular regulations I will just call your attention to so you're at least aware. So the first is CE marking, and this is coming from Construction Product Regulation, which is a mandatory regulation for every construction product in the European Union area. And all construction products sold and installed in projects in the EU must have a CE mark, and salvaged products are not exempted from this, right? So if you have a brick that you want to take from an old building which you are deconstructing to a new building, you need to get a CE mark for it in between, and that's obviously a barrier, right? So if you happen to, you know, be seeing any of the EU commissars, maybe you can take this up. But it's a political problem predominantly, so we do actually have a regulatory barrier here. But it's all not bad. So we do have emission trading scheme. And the EU ETS is regulating large steel, iron, aluminium, metals, cement, lime, glass, ceramics, and some chemical plants. And this system, of course, puts a price on carbon for manufacturing in the EU. And based on the last discussions that are being conducted, there's consideration for border adjustment as well. There's a question whether CE marking applies for national reconstruction. Is it limited to export? So this is for European Union and buildings that are built within the European Union. So and EEA. So this is like not considering export. You can export a product without a CE mark. So so much for the CE mark and emission trading. I just wanted to mention that because it's important to understand that some regulations also affect how the market works. If you are interested in product EPDs, we are also, you know, making construction product EPD software. These are some of the product categories one-click LCA EPD generator can support, and you can find them on the software website. So we cover all the main categories and then some others. So, but anyway, that's not the topic of today, so we go ahead. We have covered now the main construction and deconstruction methods, given overview of construction materials, or at least the main ones, right? So now we are going to talk a bit more about cement and concrete. And the one thing to remember, if you can only remember one thing, is that cement is made by heating limestone to high temperature. And that high temperature causes chemical bonds to, you know, break. And there's going to be carbon emissions going directly into the atmosphere from the process itself, even if all the fuel was carbon neutral. And obviously all the fuel is not carbon neutral. the cement industry is a huge consumer of energy, and it's very sensitive to the cost of energy because it's using it so much, and it's very sensitive to carbon regulations as well because it's a very big source of them. So we are here in a very energy intensive business, which is having also structural process emissions for the classical ordinary Portland cement, which is made from cement clinker. And how that works is that there's some digger going into a limestone quarry, which brings the stuff into a dumper. Limestone is crushed, it goes into milling, and it's heated in the cement kiln to these 1400 degrees Celsius, and it's let to cool, and then it's mixed with secondary things such as gypsum and other things which allow the optimization of cost and performance characteristics such as desirable for the specific application, and then it's packed, and then it's dispatched to plants. It could be, of course, also directly delivered to silos, but doesn't make any difference. And this is the source of our climate problem, really, or biggest source of our climate problem. And it's because of the chemical bond cannot be broken in a low temperature. So we need to either have alternative way of making cementitious material, or we need to find a way to make zero carbon temperature and capture the carbon arising out of the cement kiln. And neither of them are easy, right? That's why we have the problem. And if you're looking for rule of thumb, these charts may be a bit on the small side now on the screen, but hopefully you can read some of it. So if you're looking for a rule of thumb, in EU, we talk about 700 kilos of CO2 equivalent per ton of cement. And more than 1/2 of that is due to the calcination in the process, right? Impact obviously varies by region and supplier. If you're looking at a global figure, it's closer to, let's say, 900 kilos or 1 ton per ton. So it's a very high carbon impact. In the EU, it's much lower because we do have the emission trading scheme, which is putting a price on carbon, so you can't afford to do that in the same way. And then we have some lower carbon options, right? We have some mainstream ones and some more novel, and some which are actually growing quite fast as well. And alternative binders can be used and have been used for a long time. So there's blast furnace slag and other geopolymers which can be used, which develop, strength similar way as clinker. There's also fly ash, rice husk ash, especially interesting, obviously, for construction in Asia, and other pozzolanic materials which can be used. They also develop strength. You can use gypsum in concrete, and there's a range of innovative technologies which I'm not going to go into. Some of them can be found on the Global Cement and Concrete Association's website. And there's a lot of variance for cement, but the very lowest, GCPS is same as blast furnace slag. What I was going to say is that in the lower end, you can see there's a great deal of variation in the carbon footprints of cements, but these are predominantly achieved by using alternative binders, and the alternative binders do usually have a bit longer curing time. And the longer curing time is no problem as long as you design for it. But if you have to get your building erected in, let's say, 6 months, and it's not being designed for allowing longer curing time for certain elements, you could have a little bit of problem because, your building will collapse if you start to load it before it's the structures are hard enough, for example. So that's one aspect, right? So we have the cement and how it's developing strength. And then there's another aspect which is quite interesting as well. So anything made with clinker, if it's left in contact with air, will slowly carbonate, right? So the calcination reaction is reversible, partly at least, and it will start to carbonate, absorbing carbon. And the part where it's absorbing carbon is, of course, a good thing. So it's absorbing atmospheric carbon, thus reducing the climate impact over the lifetime of the building. but it's not a desirable characteristic in general because concrete is highly alkaline, and the absorption of carbon dioxide is a bit like, you know, drinking Pepsi, it's acid. So it's reducing the alkalinity, and when the alkalinity is reduced enough, it's stopping the alkalinity, which is protecting the reinforcement steel, and it can lead to the elements cracking. And when you have elements cracking, you have a major service life problem for the building or for the element in question. So the carbonation is a two-edged sword, you could say. Provides desirable climate impact reduction, but you have to be very mindful of not exposing the steel to rusting. There are some innovative technologies which allow you to work making carbonation behave in a desirable manner in the process to develop strength, but I'm not covering those today. Now we go just to the mainstream materials. And as I said, this industry is taking regulations and such things quite seriously. Recently, chief economist of US concrete industry says that climate change is a bigger threat than recessions for US cement producers. So, you know, I mean, I hope he was right. So this definitely has to change in the industry. So much for cement. So when we have this cement, we take a bag of that, we take a lot of sand or aggregates, and we mix it with admixtures and water, and we put it in a nice truck, and the truck will rotate so as to not to, you know, let the ready-mix concrete start to cure, and then we pour it or we pump it in a formwork. And if it's high up in a building, you have to pump it using a pumping equipment, or if it's you know, foundations or such thing, you just pour it, and it can be more fine, it can be more coarse depending on the application. So a lot of different variants exist. And the curing will happen then in the formwork. Usually it's evaluated, the strength is evaluated in 30 days, but you can of course set your strength evaluation time based on whatever design constraint you have. And the longer it is, the better chance you have using high amount of alternative binders. And ready-mix concrete climate impact is really not just about the cement, but it's mostly due to cement. So we are dealing here with diluted cement, basically, in terms of climate impact. So depending on the strength class, you're dealing with like 200 to 500 kilos of CO2 per cubic meter, or for a rough figure per ton basis, like 100 kilos per ton. It varies by a lot of factors and very strongly linked to the cement content in the mix. As you would guess, by substituting clinker with alternative binders and consequently trying to use for longer compressive strength evaluation times, you can significantly reduce impact of classical ready-mix concrete. So then we have precast concrete. It's the same as ready-mix, actually. The only difference is that the mold is not on the site, it's in a factory. So you pour it there and you let it cure, and then you deliver it to the site. And the precast, of course, has some advantages to it. One of them being winter conditions. So if it's winter conditions, it's much easier to manage the curing in a factory. And there's also the possibility to sometimes optimize strength development time. So some concrete plants use Friday batches. So the Friday batches use less cement because they are left to cure for the weekend for the initial curing before they are lifted. I think that's the Right, no, I forgot to say one thing. So the precast concrete also does provide you the opportunity to optimize it with, for example, with hollow cores, which is very effective way to reduce building mass for slabs, for example. Or as somebody mentioned, yeah, bubble deck. So you can substitute cement much more efficiently in a precast environment than you can in a ready mix. And the precast impact is then because the steel is already installed in the plant and not on the site, right? So the precast impact is mostly due to cement and rebar and possible insulation if we're dealing with sandwich elements. And typical impact completely depends on the function of the product in question. So if you have a column, it's obviously having much higher impact per ton or per cubic meter than a wall because its load-bearing ability is much higher. And here, as opposed to just thinking of alternative binders, which still remain important, you actually have design strategies. So hollow core is very popular for a good reason. Bubble deck, another option. You can also use other element design strategies. In many countries, delta beams or other similar type of anchoring beams allow for making somewhat thinner slabs. And of course, that's highly material efficient as well. And there's a lot of variance between such designs. But a slimmer slab is not always the best. So it depends on the overall use of material between steel and concrete. So we do also have blocks. And concrete blocks are usually massive. They have high material use and high structural load. But if they are hollow, they are not. And they are laid with like tiles, so with mortar or with reinforcement. And in some cases, they can be laid with, with kind of Lego-like bricks. That's a bit less common, but it exists, right? And solid blocks have high load-bearing ability and carbon impact as well. Hollow block work is much lighter, lower impact, very limited load-bearing ability, but it uses much less material. So in that sense, better. And on the other hand, we do have some alternative materials which provide some of the benefits as well. So leca blocks, so light expanded clay aggregate, cinder blocks, which are basically ash mixed with, concrete, autoclave aerated concrete, and all of these are lighter and do have some limitations on the load-bearing ability. However, because these are all also lighter materials, they do not have to have the exact same load-bearing ability as your classical solid block-based wall would have to. So these are the main considerations in matter of blocks. So I said this already like in a different way, but I will say it again. Not even 1% of the world's concrete buildings are deconstructed at end of life. So we have the highest carbon materials available in the world. We use them in large quantities to make very durable, high quality precast products, and then we destroy it, right? So we have the highest carbon waste you could find. It's not very clever. If you happen to be an early career professional, hopefully you will be able to have a fresh start into this. And if you're already in working life for some time, hopefully this presentation gives you some ideas what to do about it. So that's cement and concrete. We may actually be, depending on the number of questions pending at the end of the session, we may be a bit ahead on time. I'm sure everybody can accept that on a Friday. So we go to the steel and aluminium, right? So if you have to remember one thing about steel, it is made in high temperature. If you need to remember two things about steel, it is that it's having impacts because of the high temperature and because of iron ore production. And steel is made from iron ore. And before you can make steel, you need to get, metallic iron, so which is not mixture of iron and other things. And you do that in a pre-process, which can be either blast furnace or it can be direct reduction process. And in there, you actually use reduction gas in the first case, use reduction gas to remove the oxygen from the ore. So you end up with something which is iron. And once you end up with the iron, you put some additives to it for achieving better properties. You put some carbon, possibly some, nickel and other things to achieve the steel properties you want. And then you make products out of it. And it's a continuous casting process usually, or always. So it comes out as in different formats. And you can also feed recycled steel into the process, but the process actually won't run on 100% recycled steel. So you always have to have some amount of ore as well in the process for reduction. So basically when you get 100% recycled steel, it basically means 100% and read the small print as it is. So, but steel reduction, iron ore reduction and then steel making happens in two main processes, which are electric arc furnace, which is using electricity to generate temperature, and the basic oxygen furnace, which is using fuels, typically coal, to generate temperature. And at very high temperatures, higher than cement, so 1800 to 1600 respectively. And the amount of energy these plants consume is huge. So to give an example, in Finland, we do have two steel plants, one very big and one fairly big. And the very big one would need more biomass than we can supply out of Finland. So the amount of energy consumption is really massive. I mean, we do have a lot of forest, but we actually use it for forest industry. So that's why it's not enough, just to be sure it's understood in the correct way. So these are very energy intensive industries. So the impacts are directly driven by the primary steel because the recycled steel reprocessing is much more energy efficient. And to some extent, it's influenced by other feedstock, but it's predominantly influenced by the manufacturing energy mix and the process energy efficiency. So steel between Europe and China does have different impacts, most certainly, already at the manufacturing. And then if you consume it in Europe and you add transport from China, you are again penalized for the transport. Now, if you are looking into this at the policy level or global level, the most important thing is to favor low carbon primary steel. But of course, at the project level, recycling rate makes a difference too. But because 100% of the recycled steel is always going to be used because it costs the same as non-recycled, like there's no premium or such for this type of commodity, it's not going to go to waste, hence creating a strong demand for the low carbon primary steel is the most important policy. On a project level, obviously the recycling rate makes a big difference. So I encourage you to also choose recycled products when available. But if you can choose low carbon primary, even better, in my personal view. Now, Swedish steelmaker SSAB, they are looking at making zero carbon steel by 26. This is a pilot plant, which is in the picture here. So not much steel coming out of this size of plant yet. But in a few years, we hopefully can start buying it in some quantity. Of course, we need hundreds of these plants to supply the global steel demand and not just like one or two. But anyway, we have a start here. Then when we move to aluminium from steel, right? Aluminium is made from alumina containing ores, predominantly from bauxite. And the process is so that the bauxite is processed chemically and thermally to alumina. And the alumina is electrolyzed with electricity at a temperature of about 1000 degrees Celsius, right? And the electrolysis process is using cryolite, which is a rare mineral, and it's also using anodes. And the anodes are often made from carbon. And of course, the anode is, in most processes, consumable. So there's process emissions coming from anode consumption. So when the carbon-based anode is like wearing as part of the process. And furthermore, there's F-gas emissions from the process. So there's again process emissions coming, but the predominant source of emissions is still the energy demand for aluminum processing. So if you look at, let's say, primary aluminum, about 1/3 or so are all types of, or 25% are process emissions of other nature than electricity. And when you end up with aluminum, you heat it, you cast it, you can cast it into sheets, ingots, wires, billets, whatever, and then you ship it to somebody who makes other things from it. I think that covers the aluminum. Aluminum processing can use also other inputs than bauxite, but it's the most common by far. And the aluminum process generates huge amount of byproduct called red mud, which is not harmful, but doesn't have any commercial application or major commercial applications as well. You can recover some stuff from it. I think that's the main thing about aluminum. Sorry, I did forget to say one thing regarding steel making. So yeah, the steel process actually generates blast furnace slag. And the blast furnace slag that you generate here is the same one that you mix into the, or you can mix into cement to reduce the carbon impacts of the cement. So I forgot to say that in the previous. So much for aluminum manufacturing. That's the predominant process. And the aluminum impacts are very high. So if you are looking at just primary aluminum ingot and you get primary aluminum from China, you're dealing with about 20 kilos per kilo. So the most carbon intensive of any construction raw material used in quantity. If you look at the average primary aluminum used globally, so you of course have different locations. So it's made in Canada, it's made in Norway and so on, and Siberia, right? So which have a lot of water power and or hydropower, and the average globally is a bit lower for primary aluminum. And aluminum is having some traction for labeled low carbon aluminum, and London Metals Exchange is looking at setting a trading commodity platform for low carbon aluminum, and we are dealing with below 8 kilos per kilo. So certainly it's not a low carbon material at this point. But if you consider the recycled aluminum, it's not comparable at all in terms of emissions. So recycled aluminum is always far lower in terms of carbon impacts than primary aluminum, even if made with low carbon process. I did forget to mention that there are a lot of investments and technologies which are being deployed in the aluminum production industry among the handful of big aluminum makers to create sustainable differentiating aluminum, which would reduce also the process emissions. So it's one of the hard to abate industries, and there's significant investment and R&D going into it, as is into these other industries that I mentioned. If you like to read about aluminum, there's a white paper from last summer on our website. You can find it there. Applications are in facades, windows, partition walls, and such like. So maybe it answers also some of the questions that you could have on construction products which are assembled, which are not covered today. So to recap on metals, they are extremely recyclable, but the focus should still be on reuse as product if possible. If not possible, then of course forget it, right? and favoring low carbon primary production, because the scrap covers only a very small fraction of the global demand. And there's no question about the scrap being used. It's all gonna go into use. So for steel, it covers, like the scrap covers 25 points of the global demand. And aluminum scrap covers 30% of global demand. There's a question whether aluminum from Russia is preferable to that from China. I do have to answer that now because it's so attractive question. So it is if you buy Rusal's alloy aluminum, which is made in Siberia with hydropower. So that is about 6.7 kilos per ton, and Chinese is about 20. So, 3 times better. That's the case of Allow brand from Rusal. They also have other smelters which are not running on 100% hydropower. So, so much for that. Okay, so about the design for disassembly, right? If you are able to move a steel building in your carrier, you are not breaking ground. So the first major steel frame building that was ever relocated was Crystal Palace. Huge, sadly lost building, was destroyed in 1936. It used to be in Hyde Park for 3 or 4 years for as a pavilion for exhibition. But the people thought it was such a lovely building, they didn't want to take it down, so they bought it for princely amount of half a million quid and moved the whole building to Sydenham Hill and reconstructed it there. So this can be done with steel. So your job is to do it and to make sure that it can be done easily. And I would also encourage you to consider whether you could actually find something that you could reuse as products as opposed to recycled material in case you work with steel. I can't obviously cover all aspects of a circular design, but if you're minded to learn more about this, there's, for example, a good ebook about this by 3X Architects on circular design for all structural materials with visualizations. We have covered steel and aluminum. There's also copper, there's zinc and others. They are used in far smaller quantities. I will just mention the one thing about copper is that copper's predominant application is either piping, or it can be also, or it's obviously also electricity transmission. So if electricity is the question, then of course the conductive loss or conducive loss is a thing to consider. So you want to not to just reduce the amount of copper in your cabling, but you also want to minimize the electricity losses, so you have a life cycle balance between the conducive losses and the amount of copper you put in your building. The rest of the materials, metal-based materials, are used in so small quantities that they don't need to be covered separately, at least in my opinion. So we go to other construction materials. In this category, I won't cover everything. I will just cover wood-based insulation. I will cover refrigerants, bricks, and I think 1 or 2 more. But there's plenty of more things that could be discussed, but I won't, considering the time that was planned for this session. Wood and wood-based products. They come from nature. The carbon sink, or let's say carbon storage, has been created in the what's called biosphere in LCA sense, right? And it moves to technosphere when the wood is cut. So when the tree falls in the forest, even if nobody hears, we create a nominal carbon storage. Obviously, it was there all the time, right? But it's just because it's transferring from the biosphere to the technosphere, we have now a carbon storage. And this carbon storage is a positive thing. So the question here is, how can we preserve the carbon storage? And what do we do with the wood in other terms as well, right? And if you have a wood project or wood-based project, there's some things from the carbon balance point of view that you really should consider. So the first thing is, don't use illegally logged timber or timber from unsustainable forestry, for example. So if the biosphere is such that, for example, it's final logging and it's not going to be replanted or unmanaged or illegally logged or such like, there may not be any more wood growing, at least in significant quantity, to generate further carbon storage. So it's a very significant loss. And it may also lead to soil carbon content loss. So then you can have a really bad baggage in the timber actually. Similarly, if you have this timber with this biogenic carbon, if you let it get landfills at end of life, when it gets buried in a landfill, I'm assuming we talk about managed landfills, right? And even if unmanaged, it will start to decompose, right? And this will cause huge methane emissions. And these methane emissions, of course, they completely destroy the carbon balance that was so positive to start with. So on the downside, the third thing is, if you don't need to have treatment or painting, for example, for fireproofing or zoning reason or other, think about it. Do you actually have to have it? On the bottom corner here, there's a weathered wood facade building, and wood weathers really nicely, right? So you just have to make an aesthetic choice about that, right? And here I think it looks pretty good. And you never have to lift a finger to keep it in that shape, right? So far less money spent. Painting is quite, labor-intensive process, cost of money, and it has environmental impact. So if you can actually let it weather, that can be quite interesting opportunity. And think about this carbon storage from the point of view of whether you actually are going to be securing it or if it's just an interim thing here. So on the do side, even if you make wood building, do consider material efficiency. End of life, I did talk about that at some length. Wood in many materials, many applications need additional layers. So if you, for example, do timber floors, you typically need 2 gypsum boards for fireproofing. And then on the top, you need something massive. You can either use like 5 centimeters of concrete. Some are also using gravel just for mass because the step noise is very significant otherwise. And so on and so on. So you have to consider all the layers you need to put in your building to make a fair assessment of it. And importantly, also timber is lighter. So mass timber is less light than a stick frame, right? But it's always lighter than equivalent concrete. And so do consider the mass reduction, right? So timber or steel for that matter, if it achieves a lighter building, is very desirable for locations where you would have very heavy foundations or you have earthquake risks, because if you can avoid having a lot of mass, then you don't have lateral shifts in case of earthquakes, and you don't have so much pressure in case of, just tricky foundation conditions. And so for timber, as for everything else, the good practice instead of landfill is to reuse it as product. If you can't reuse it as a product, burn it and use the energy, for some productive energy application. Of course, depends on your location having power plants which take mixed waste, but there's also a global market for this type of waste food incineration. Then going to typical impacts. So sawn timber has naturally lower impacts than CLT, glulam, or LVL, which are all more processed and which use about 9% or 10% or such like proportion of glue, either fossil-based glue or bio-based glue, but it doesn't matter, chemical, which is much more energy intensive to make than wood, which is growing in the forest. If you want to get lower carbon products like CLT or other, You may have some differences between the products as well, between manufacturers, but you should definitely be aware of accounting methods, because the bio-based or biogenic timber is a topic that some people, let us say, try to take more advantage of than the LCA standards would permit to happen. So don't trust everything you see blindly. That's the main things about wood-based products, I think. I do not cover here like plywood, particle board, oriented strand board, and such like. Those are derivatives. Similar principles apply. Then insulation, right? With insulation, there's really a vast range of different insulation products available. So you have mineral-based. We can start with foam glass, glass wool, rock wool, perlite, vermiculite, expanded clay, and so on. And then we have a lot of chemical-based and combined. And in terms of plastic-based, we have several typologies. So we have EPS, XPS, PUR, and even others. If you want to read about them in detail, Ecopassive House's website has these summaries, which are quite interesting, I think. It's not necessary to understand all of them, really. The main insulation materials usually would be glass wool, rock wool, plastic-based insulations. You can also use cellulose wool and sometimes other things, but the volume of insulations tend to be those. There's also spray foam, and my suggestion is that don't use spray foam. So with insulation materials, it's a bit similarly to the wood one. Wood being a positive thing in many ways, the main thing is to avoid the stupid things. Insulation is good because it saves energy, so do avoid the silly things here. The most important thing is to avoid spray foam, avoid it altogether if you can, and avoid any foam insulation with unspecified blowing agents. If you are operating inside the European Union or EEA, there are many blowing agents which are prohibited, so they cannot be used. But if you are building outside of EU and EEA, you should not allow use of any foam insulation with unspecified blowing agents. And you should review what actually is used before you accept use of foam insulation of any kind. So just don't do it. And even if you are in a civilized country, you know, like Canada, you can buy them, right? These and people use these extremely high GWP blowing agents. And in a Vancouver residential building, like if I remember correctly, 1 square meter of the roof insulation, which was form of a spray foam, was equivalent of like 20 square meters. So like of the building, total building impacts denominated by floor area or something. So it was, I can't remember the exact ratio anymore, but it was completely insane because not every jurisdiction regulates their use. So be really mindful of that aspect. Second, if you can use insulation without gluing it to the moisture barrier or to anything else, do avoid it so you can recover it, because it could be recycled and reused. Consider low carbon or carbon storing insulation materials. I will waive to give an opinion on that right now, because it really would depend on your location. Some locations do have a bit different supply. Insulation is very local material because it's expensive to transport for most type of insulation. And the two things to consider in particular are the total insulation layer thickness to the total structural material demand. So because some of the insulation materials thermal performance varies. So with some materials you can achieve similar thermal performance with a thinner, and with others it requires a thicker layer of insulation. So you should understand whether it's advantageous or not that your walls become, you know, say 80 millimeters or 100 millimeters thicker or so So what does it mean actually? Because if you make your walls thicker, then actually your ground slab and your floor slab and such like also grow. Also, don't reduce insulation so that the energy use growth would be uncontrolled. So obviously we do use insulation to limit consumption of energy. And it's much easier to recycle the insulation waste on the site than at the end of life, because you're not going to be there. So at least try to recover the clean insulation waste. Well, of course, if it's built on site, but also in the factory, it's very desirable when you are doing prefab. Those are the main things to consider for insulation materials. So I will not recommend any particular type of insulation. We have done some region-specific benchmarks for some regions, but I wouldn't be able to claim that it's a global rule of thumb. So I'm not going to suggest anything at this point. Then we go to gypsum. Gypsum is recovered both from nature and from the flue gas of coal-fired power plants. And in Europe, the flue gas recovery is a very significant actually source of the gypsum use in total. And gypsum is used in several types of construction products. As it was mentioned before, it's mixed also into cement and such like, but it's also used for specific construction products. Mostly these are the finishing products because gypsum doesn't have structural properties. Gypsum boards, they can be used for ceilings, they can be used for walls. When they are used for internal walls, they are installed with steel or wood studs. And here again, I do encourage you to ensure adaptable and dismountable installation. Gypsum boards are quite massive, and they can be used in quite significant quantities in a building, especially in a wood building. However, they are required because they provide mass, and that provides acoustic performance. So you don't actually have to know what's going in your neighbor's bedroom or in your floor above yours. So they do provide important function, and the mass has to be there. Of course, there may be some alternative ways to add mass to a building without gypsum, but predominantly this is an application that's used today. So you have double gypsum boards on office walls, for example. Our office has it too, and that's also for acoustic purposes. It's used in finishing plasters, for leveling non-load bearing surfaces, and then it's used as flooring screed as an alternative to cementitious flooring screeds. Some pros and cons for both. Gypsum-based screeds would be, I would say, my estimation is that it's a bit lower or lower share of the market than the cementitious flooring screeds, but both are used. That's it for, I would say, for gypsum. Gypsum is also having process emissions in the manufacturing. Temperatures for gypsum are not as high as for any of the previously mentioned mineral-based products, but doesn't come emission-free, certainly. Then very shortly about float glass, right? And float glass is made from silica sand and other stuff, and it's made in an integrated process that has a temperature of up to 1600 degrees and goes through a number of process steps. And once made, it lasts for a very long time. Very good overview from Saint-Gobain, India on the glass manufacturing process, if anybody wants to read up. The glass manufacturing doesn't have any quick tricks for reducing emissions. So this is very much a pure R&D problem. And the other thing, which is quite interesting with glass, is that once you made it, it lasts for forever. So the glass windows which were made for Palace of Versailles, they are still in use, right? So if you can reuse windows, or you can reuse other glass-based elements like partition walls with with windows, it's very desirable and very good in many ways because the material hardly degrades, of course, except if it cracks. Right. Oh, there's a very good comment about trying to increase building air tightness with spray insulation filling gaps and what was stated about not using spray insulation. So sure, improving air tightness is a good application. So then you would just control it, but it wouldn't be used in significant quantities in such case. But then you would need to know what blowing agent is used. Glass is recyclable, but with some difficulty. So there's a lack of, let's say, commercial end application for recyclability. However, I would say by far the most sustainable choice still with the glass would be definitely to try to reuse it as a product. Like there's no quick way otherwise than that to work around the glass energy intensity of the process. So then bricks. Bricks have a climate impact themselves. They are fired from clay, or if they are fired, right? And they are laid using cement-based mortar. So if you lay bricks, always consider the impact of mortar as well, because it's used in relatively significant quantity. And the screeds and mortars that you use, they may have a meaningful contribution to the choice of the facade material. The types of bricks, fired clay bricks, is clay. There's no process emissions from chemical reaction. So it's just the fuel really. And if you actually have a biogenic fuel, you have no impacts. So that's pretty interesting, let's say, approach. And some plants are able to do that. So those are very low carbon products by comparison. There's also air-dried bricks, not big in Europe, but a very interesting approach in some African countries where also the cost of firing bricks may limit, let's say, sorry, I misspoke, African, also like other hot temperature countries where you don't have to always build tall. So air-dried bricks are also used in a number of regions. They are not load-bearing. Sometimes cement is added to them, and of course that pretty much destroys the equation. So it basically makes them clay-based concrete blocks. So they are then environmentally undesirable products. Then we have reclaimed bricks market. It's a small market, but very good one. So bricks last forever for human condition purposes, right? So 1,000 years is no problem. Color, of course, will change over time. And you can have reclaimed bricks, which are separated from the mortar. And of course, this mortar separation is a cost. And there's this kind of aspect to it. But what's been recently done, and I encourage everybody to consider, is that because the brick wall can also be sawn in sections with the existing mortar. So just, take 1 meter by 1 meter sections and pile them into your new building, and you have far less mortar demand and far less cost, and I would think a very advantageous setup all in all. Cheaper to dismantle the old building and all that. And because this type of brick walls, they are available in pretty large quantity, because at a certain time a lot of industrial buildings have been built using bricks. So if those industrial buildings no longer have any use, you can find plenty of brick walls to chip to bits with some luck. So that's it for the bricks. Then we talk about, very shortly though, refrigerants. So if you are in the mechanical design, or if you are advising on sustainability, passive systems are of course great. So if you are able to use passive shading, natural ventilation, or any such thing, is far better from an energy point of view. but it's of course not enough for all types of buildings and all locations. So very likely for some type of buildings and in southern, let's say, and tropical conditions, always you will have air conditioning. And when you have air conditioning, you're going to have refrigerant fluids. And when you have refrigerant fluids, they will leak to the atmosphere. And the choice of refrigerant is very important. In the European Union, we have a lot of refrigerants which are prohibited. If you are outside, then there's probably very, very bad stuff also used. Now, we have here some charts from a CIBSE study, which was done in a European context. So the worst types of refrigerants were not considered. But here we have up to 18% for an office building using EU allowed refrigerants from the life cycle impacts just coming from the AC refrigerant leakages. And that's obviously massive, right? So we are dealing here with potentially very significant problem for buildings which produce chilling. Just to put this in a context in a different way, in my summer cottage, the small heat pump which is installed on the wall, it has embodied carbon of about 50 kilos, but the GVP of the refrigerant fluid load in it is about 3,500 kilos. So, you know, it's leaking and it's leaking, and every year it's leaking more than the embodied carbon of the installed units worth. So more information about that can be found in the CIBSE article, and there's also a technical manual from CIBSE, which is TM65, if I remember correctly, and it provides quite detailed methodologies about these things as well. And just to give a total figure, this is very outdated, I have to say. I couldn't find quickly something more recent. So the total refrigerant leakage global warming potential in EU was estimated at over 100 million tons of CO2 equivalent for HFC systems in 2001, right? So this is more than the entire, well, Finland is not a big country by capita, right? So, but this is much more than the Finnish annual carbon emissions from all sectors, including our steel export and everything. So, yeah. Mind the refrigerants. So we have covered all the construction materials that I meant to cover. I have not covered openings, doors, windows, wall, partition walls. I have not covered flooring. I have not covered many plastics. I think you can look into those a bit later. But if you already do a great job on the cement and concrete, steel and aluminium and a few of the other things that were discussed, we are a long way towards really decarbonizing our built environment. The homework for today is a very simple one, as it should, because you know, you have other things to do on your weekend potentially. So look up low carbon, local or regional manufacturer specific EPDs for ready-mix concrete, structural steel, aluminum profiles, and cross-laminated timber or glue lamp. Just check what can you buy, who's making them, and what makes you think that they are low carbon, right? So maybe your local supplier is not favorably positioned in this matter. If you happen to have no local ones, add some transport distances to get them to your location, and you should have an idea of the impact in the specific cases, so you can get your own reference values for the impacts for these products that we have discussed. I will be happy to answer any questions, but I believe my colleagues have done a much better job on that one than I ever could have done. So many thanks. Antti, Samantha, Veselin, Sean, and thanks everybody for listening. I hope this is important. I hope this has given you some important information on on understanding carbon impacts and being able to act on them in the future. Right, I will go to the, not wrapping up right now, so I'm answering the question on the refrigerant chart. So the refrigerant chart showed the share of impacts of the whole building lifecycle carbon impacts between the building, between the HVAC systems and the refrigerant leakage, where the refrigerant leakage is the blue section here, and it's having 3 scenarios with 10% leakage per year here, and a medium impact scenario lower and low impact scenario lower. Yeah, so that was the chart. So yeah, I will be staying online to answer any remaining questions for some time. And in the meantime, many thanks for everybody for joining. Hopefully it was useful, and see you soon in the next sessions on the next week. There's 2 questions about the party of after completing the summer school. So we have considered having a party at the office, but I'm afraid we can't invite any participants to this particular party owing to the restrictions in place. And so I do encourage you to celebrate your certificate though. Proportion of refrigerant for data center. Sorry, David, I can't answer off the cuff, and also would probably depend on whether you are able to recycle the surplus heat, right? So I can't answer that off the cuff. Sorry. But it's not negligible. That's kind of a fact. All right. It doesn't seem that more questions are. All right. One more question about the homework. Which are the information from EPDs? Location, kilometers, if not local or region. So just try to find an EPD that's made in the country where you are. If it's a very large country, try to see if you can find a regional one or like more local one. And you might find the factory location in the EPD itself. If it doesn't state the factory, if it's multiple factories, then you can just use assumption. So don't like stress it, but it's more like to understand whether you actually have local supply as well of certain material, because not everything, like not every country has local supplies for these things. There's a question about recording and slides. Is it tomorrow morning? Answer is no. Monday would be the day. There's a question about glass is robust material as plastic lasts for centuries, but glass is not used as a consumer product container anymore, right? That probably makes the biggest difference why we don't have a glass pollution. So there would, of course, if the glass was only consumer product container for food and ice cream and such like, we would probably have a glass pollution problem, but that's not the case. Construction waste management is a bit more sophisticated than consumer. All right. I believe we are about ready to wrap up with this. Once more, thanks. Have a great weekend. The webinar ends. Bye. And thanks for listening.